at least some of you must be wondering, ASET and mathematics and a mathematician. So at least I should put the record straight. Those of you who have seen or heard, some of the most wonderful talks given by mathematician. In case you are not present, I will just say a few of those. Personalities on Indian mathematical scene by Professor M.S. Raghunathan on 17 January 2003. And he repeated with another great one, that is said mathematics and scientific mellow on 3rd December 2004. And then we had sum of squares and 290 theorem. I'm sure all of this many of you remember, by Manjul Bhargava on 27th February 2009. And then the one that came close to my at least field of study, the error correcting codes by Professor D.K. Chaudhary from Ohio State University. That was on 20th March 2009. So this is not the first time that ASET hosted a mathematician, and today we are going to host proudly another mathematician, Professor Nitin.
Probably, yeah. Probably. Yeah, you probably. Choice of words.
Thank you very much, and thank you for this kind invitation to speak in this ASET colloquium. My theme is very historical and evolutionary, and so I have put a picture of evolution as we had been taught in school that there is some kind of lower creatures and they evolve and they become something. And there is a kind of progression perhaps, and all these people are safely dead, so they can't say anything, and I hope nobody takes offense on their behalf. So this is Pythagoras, this is Descartes, who was a very cool character. And this, of course, you know. So the discovery I made, discovery in the sense, discovery just for me, others might be knowing it all along, was that Euclidean geometry also underwent an evolution. And this evolution started in the story that I am going to tell with Pythagoras long ago, 500 BC. And it went on till about early 20th century. And then various things happened in the course of this evolution. New technology came cheaply, which was not available to the earlier people. So they could do things which others could never have dreamt of. And that's where it's an ASET colloquium appropriate topic with respect to technology. And a particular machine was of great use in all this. The machine is called the Mackey machine. And Mackey has nothing to do with monkeys, you know. The remarkable thing was this long evolution, which took 2,500 years, was repeated, uncannily repeated, in a very short span of 50 years in physics. And roughly ending at the same time, both things got repeated. So this I found very surprising, and then I remembered that there is some slogan, recapitulate something, which I looked up and it turned out to be ontogeny recapitulates phylogeny, or maybe it's the other way around, which is something about how the long evolutionary history of a species or of different species, their succession, whatever, gets rapidly repeated in the embryonic history of a single individual. Something rapid repetition of history. So that is what these pictures are about. So I entered that, recapitulates, blah blah blah, and then on Google and on Google Images, of course, because you can quickly understand what it is by looking at the pictures. I realize now that instead of Googling a word and reading the text, it's easier to Google for images, and then you quickly see what is there. So it produced various pictures. All those pictures were roughly the same picture, and that was this. Except the last stages of evolution I have added. Alright, so with this historical introduction, let me begin the talk. So this being a math talk, I am going to use Blackboard heavily, but I have put on this slide number 1. This is for some technical reason I have been asked to say clearly every time I change the slide. Okay, so and I will write many things on Blackboard, but the theme of this first slide, and I have 12 of them, so I have to roughly run through them at 5 minutes per slide or faster. This goes back to the really ancient history. I hope this shows. Sometimes it shows. Natural numbers everybody knows, rational numbers also. But the real numbers are something new. Real numbers were made by Dedekind in 1860. Now we are all very familiar with real numbers. They are those infinitely going on decimals. But really real numbers are not that real. The name is a giveaway. There must be something guilty about them that people chose the name real numbers. So like they doubted the reality of those things. Anyway, they are quite complicated, sophisticated objects. And so even today you can ask questions about real numbers which can baffle students. And many more questions which can baffle everybody. Okay. There are lots of things not known. Even the size, what are the sizes of systems, all kinds of things. Unknowable, some of those things are unknowable. Anyway, so ancients did have real numbers. Real numbers have certain property called completeness. So those of you who have studied some mathematics know that bounded sets have a greatest lower bound or a least upper bound. This completeness property is of bounded sets. It requires sets. Even to articulate this property is not possible without modern mathematics. Ancients didn't have sets. So making of real numbers also involves sets. To make one individual real number, you have to invoke sets. All such real numbers themselves form a set is another matter, but to make a single real number, you need sets. So of course they didn't have those, they only have rational numbers. But in recounting this history, I am going to take today's vantage point. So I am going to assume that you know all that we know today. And that's a way of making sense out of history. So one can understand what those people were trying to do, even if they couldn't have said it, but that's the point of view I'm going to take. Looking back at history, equipped with all, with 20/20 hindsight or whatever you might call this. So let's come to Pythagoras. In 550 BC, he didn't have real numbers, and what he proved was, this is impossible. You cannot have p square upon q square to be equal to 2. This is impossible. Whatever p and q integers you take, p square upon q square will never be 2. P square cannot be 2 times q square. Which is a way of saying that root 2 is irrational for us. For him, it meant there is no root 2. Because numbers are only rational, so that means there is no root 2. On the other hand, you proved another theorem, the right triangle theorem, and the right triangle theorem said that if I have this triangle, this is 1, and this is root. So paradox, right? On the other one hand, there is no root. On the other hand, his own theorem says that this distance should be root 2. So what's the conclusion you draw? The conclusion you draw is there is no such thing as distance. Some segments may have distance, p by q, but others may not have. Yeah? So you have to do without distance as a real number. They do not have a number system strong enough to support the notion of distance. They would have liked clearly to have one, but they had no clue how to go about it, and this took 2000 years. Okay, but this didn't stop people from going ahead, and so Euclid tried to put geometry on a firm axiomatic foundation, had to do it with no distances and lengths. So how to do it? So he must have thought in a very common sense manner. He might have said something like, okay, here's this. Are they of the same length? And so there are two answers. One, each thing has something called length, which is a real number. For this, there is a real number. For this, there is a real number. Let's compare those two real numbers in the Platonic world of real numbers. This is one. Second, as a practical person, how would you answer this question? Yeah, like this. So you have moved it, or you have moved this. So what you need is motions. Your space should have some motions in it, which you can apply to specific figures and move them. So these motions is what Euclid relied on. And very specifically in Euclid, in his book Elements, there is mention of motions, which is the idea behind congruence. So if you can move one thing so that it goes and coincides with the second thing, then those two things are congruent. And practically speaking, how do you measure the length of anything? You take your measuring rod and just keep on moving it. So that's what is there anyway behind the practical idea of attaching a number to some distance, length, whatever. So that's what he did, but he axiomatized all this. And now that led to something fantastic. But to realize that what these motions lead to took 2000 plus years. So sometime in around 1750 or so, mathematicians realized that these individual motions or symmetries or whatever they are can of course be combined. You can take one motion and follow it up by another, and follow it up by a third. And then there are some obvious properties. There is a motion of keeping everything where it is. It's called identity. Or you can undo any motion. You have the reverse motion. These are exactly the properties which define a structure called a group, which all of you have studied in college. Some of you have forgotten that you have certain entities which you can combine, and then there is identity and there is inverse. So all these motions form something called group. Now this you will see even in old physics books that these transformations have group property and they leave it at that. The real important step is, if you look at the group of all possible motions, so the word group is a collective noun, right? Group. So the important thing is to consider all of them together, not one motion at a time, group of motions. So there is something very pervasive about these different motions put together. This group has its properties as a group, which are not property of any individual motion. This is called group theory. This group has properties of its own, which are at a different level, which are properties of collections of motions, which can be composed, for which they are inverse, etc., which are not reducible to properties of individual motions. So this group theory came into being, and then they realized that symmetries of anything, why just Euclidean something? Symmetries of any structure form a group. So most importantly, this was realized for solutions of a polynomial equation, and you get various roots. When you try to solve a polynomial equation, you get various roots. You may try to interchange the roots, that's also a symmetry. You try to permute some things, that's also symmetry. You can undo the permutation, the reverse permutation. You can have various threads and you can wind them around each other. Then you can do the reverse winding, or you can do winding and follow it up by another winding. That's composition. There are all kinds of groups. So the great discovery made by somebody called Galois, who is world famous, of course, we have heard his name, was that properties of this group can shed light on how to solve those equations. This was something completely new, that individual motions form a new structure called group, and properties of that group tell you something about the whole thing. So this was around 1830, and then something else remarkably happened around 1870. Felix Klein, again I hope his name is known outside mathematics, gave a lecture in the University of Erlangen, where he was newly appointed as a lecturer, and it was the custom in German universities that a newly appointed lecturer gives an inaugural lecture. So he gave his inaugural lecture, and this inaugural lecture he said that in Euclidean geometry there is a group of motions, but there are other kinds of geometries, and they are all distinguished by the groups of motions. One group of motion, one geometry. And what do you study in that geometry? Okay, I am running ahead of the story, but this is most important. He said what you study in that geometry is what are the properties invariant under that group. this group acts on various things associated with that space. This is going to be the recurrent theme of this talk. And you look for all those actions and their invariants and so on. So you try to recast geometry in terms of the group and the invariants associated with them. This is going to haunt us because this is where physics is stuck today. I'll come to that at my last slide. This is the great challenge before the young generation, that how to find a paradigm which goes beyond this. But then, so Klein brought groups and behavior under such groups as the central theme of geometry, and then studying group actions and their invariants side by side with Klein's work was already a very, very important theme in algebra. And there was this thing called invariant theory. There was a man called king of invariant theory. His name was Gordon, and he had a student called Nitsure. She is one of the greatest mathematicians. There is no point saying she is one of the greatest woman mathematicians. She is one of the greatest mathematicians who happened to be a woman, and but she had to face great difficulties because of that. So this woman, Nitsure, in 1915, she was very young. She had just finished her PhD. And she was invited to Göttingen by Hilbert because Hilbert thought that the efforts in physics require some understanding of invariants, and here is the star student of the king of invariants column. So Nitsure went to Göttingen, and then Einstein came there and gave a talk, and Nitsure was in the audience, and Einstein spoke about his general relativity theory in the making. And this one was immediately at it, and she already described how should conservation laws look in physics and how they should look in general relativity. She already arrived at these conclusions, wrote a letter to Einstein. Einstein wrote back a letter to Hilbert saying, I received a letter from Fraulein Noether, who really understands everything deeply, and the older people in Göttingen should learn from her. Okay, this is exactly what happened. Later, Nitsure went on to found one of the most important schools of modern mathematics, and her students made fantastic progress in everything. But then, let's go. So, okay, here's suddenly a technical page. Let's go. Coordinates. So now I'm running ahead by 500 BC to 1600 AD. By that time, people had become familiar with real numbers, so they didn't have a definition. And they decided to begin using them in geometry. So Newton used them in physics. Everybody started using real numbers, though Newton was very careful. Even though he used real numbers in doing his calculus, when he wrote his Principia, he went back to the Euclidean style of axiomatic to make it look respectable. But that was the transition period when people had bought into real numbers and were willing to use them. So one of the first things that it did, and that was done by Descartes and Fermat, who are the founders of algebraic geometry, is to make coordinates. You study geometry using coordinates. So there is a method of laying out coordinates. Everybody knows how to lay out coordinates. The first thing is you choose a point. On the Euclidean plane, all points are equal. So your choice of a point is very arbitrary. This is very important. Whatever distance here, chosen, you mark, and then you lay a line perpendicular to it and make this particular grid of lines, etc. etc. This is how you lay out coordinates. Now, in terms of these coordinates, you can write what are the motions, and I am going to write what are the motions. I am going to put some extra structure to simplify on this plane. I am going to take the oriented plane, meaning my plane is somewhat more than what Euclid had. In that, I distinguish right-handed from left-handed. That will keep my matrices. So, if I have some point, I can call it x, and this x is really x1, x2, and I send x under my motion to ax plus ax. Where this a looks like this: cos theta, sin theta, minus sin theta, cos theta. And this a is another set. A. So this x is x1, x2. So all of you are familiar with what I am doing. I am translating my origin and I am rotating by this angle theta. Such things form a group, and I can write this transformation by the symbol AA. And if you take another such and try to compose them one after the other, out will come this law. This will be A plus B, and this will be A, sorry, this will be A plus AB, and this will be AB. This is a little one-line calculation you can do of taking two such composition, two such operations and carrying them one after the other. So for the few mathematics students in the audience, this is called a semi-direct product. And the notation for this is R2 SO2. Okay. So this is the group semi-direct product. And now, if I have another coordinate system, x prime, pi prime, whatever it will be, x prime, y prime will be related to x and y exactly by such transformations. Conversely, I take one coordinate system, apply this transformation, I will get a new coordinate system. So the coordinate systems are exactly related to each other by these two. So therefore, Euclidean geometry takes this shape. Study those properties of R2 and structures, shapes, whatever on it, which are invariant under this rule, which means they should look the same in terms of all coordinate systems. This is the invariance property. Those things should look the same. For example, line. Lines have linear equations in terms of any of these coordinate systems, or circles have the same kind of equations in all of them. Now, this is related to the Pythagorean metric. Due to Pythagorean theorem, this square plus this square is equal to this square. You can give such a metric on that plane, and you can describe these motions as exactly all those transformations of the plane which preserve this metric. And then one can also say that, oh, geometry, forget all these coordinates and changing of coordinates, just take this metric and you make up everything which is in terms of this metric, that's Euclidean geometry. That's another way of saying it. One way is about changing coordinates, talking of transformations and invariance, another is purely in terms of metric. Now, this word I should explain, metric gives rise to the affine structure. This is important here because Galileo's first law is because to take care of this in that right setting. Affine structure means the presence of distinguished sets called lines. And line is describable in terms of metric as the shortest path of going from somewhere to somewhere. That's a straight line. So lines are born out of the metric. So all your transformations preserve lines because there is no metric. Okay. There is something more that you can do on, and this is technically important, I will say it rapidly, there is something more that you have to put on Euclidean space. So I already talked of orientation, that means to distinguish between right-handed and left-handed things. There is something more is called spin structure, and it takes a long time. I think in a typical physics classroom they spend at least a lecture explaining spinors, or even more perhaps, yeah? Yes, so I won't straight away explain what it is, but I will give some hint of what it is. When you rotate something fully 360 degrees, you are back. I just rotated it 360 degrees and it's back, but my hand is all twisted, right? I rotate it once more 360 degrees and my hand is also straight now. So there is some other hidden structure which when you rotate fully instead of coming back, has only half come back, and when you rotate this twice, it comes back fully. Such a geometric structure is present in a hidden form here. Making that explicit is what is spinors. Using it in physics is very important. This kind of structure, spin structure, was first discovered by Elie Cartan in 1913 and was used by Dirac for his modeling of electron in 1928. Look at the shortness of the time interval. So between early steps in mathematics and early steps in physics, thousands of years pass. Later on, the time span gets more and more compacted. So, the groups, there are certain groups called spin groups, which tell you how you have changed your coordinates together and how twisted things have become. These are the groups. I will not talk more about them, looking at the time and the audience. I will go easy on that. Now, let's come back to Euclidean geometry. The question is, what do you want to study in Euclidean geometry? Now, Euclid studied intervals and triangles because he had to frame everything in terms of actions. You might want to study a mountain, right? Here's a mountain on the Euclidean plane. Here's another mountain. You can ask questions like, is this mountain congruent to that mountain? Which means, is there a motion of the Euclidean plane, translation, rotation, so that these two mountains exactly coincide? You can ask any such question. But Euclid had no way of posing these questions because only figures he could deal with were made up of points, circles, lines, because his actions could only deal with those things. But once coordinates were made, once real numbers are and complex numbers are available to you, you can look at far more number of figures. So you can ask far more questions of the right kind, of the figures which interest you. After all, who is interested in triangles? We are interested in all kinds of nice other things, not triangles. Okay, so simplest Euclidean space to think of is the oriented Euclidean line R1, one-dimensional Euclidean line. And all of us are very familiar with one-dimensional Euclidean line, and that is our experience of time. Time is a one-dimensional Euclidean line in our experience. And in time, what happens? If you only want to look at subsets, then there are intervals of time. Yeah? There is no spatial origin of time. You can take an interval. I am taking it oriented line, meaning future is distinguished from past. So there is a translational symmetry. You look at something and then play a video and then watch it 1 hour later, it's the same. Time translation. So are there any basic figures in time? One should study functions. Sound is like function is like a figure on the time axis. So your sound vibrations you have to treat as a certain figure in this one-dimensional Euclidean space. So question, what are the basic figures? And the answer is obvious. Basic figures are the pure notes. Shuddha swara of various frequencies. Shuddha swara not in the Hindustani sense, because those are not continuously distributed. Every possible constant frequency is a pure note. Okay? So one should take pure notes as the basic figures on this one-dimensional Euclidean space. On them, how does time act? Time acts on them by just a phase change, that's all. And all of you are familiar with how to model this kind of vibration using complex numbers instead of real numbers. So that phase change is just rotation of the phase, which means multiplication by a complex number. So all these pure notes you think of in complex terms, and then they are all eigenvectors, eigenfunctions for the translation operator. So Fourier, who was a good friend of Napoleon and is known for doing all kinds of different things, was the one, the ideas were there, Gauss and others were already talking of such things, but Fourier carried this to some completion, saying let us analyze all possible functions in terms of these pure notes. And then this is called Fourier analysis. For a function ft, you can find out the components corresponding to various angular frequencies. And that's that f hat omega, that's the magnitude of the component of that sum. If you know the magnitude of every possible pure note, and since we are working in complex numbers, this includes its phase, then you can reassemble that sound. That is the notion of inverse Fourier transformation. Okay? So now I am going to rapidly run to the next step, but that's really very important. So these are the square integrable functions on R1. Now the notes, the sounds that you take should be such that they should be there early and then they should do something and then they should die out again. This is the kind of sounds that we are interested in. The total integral or square integral is finite. This square integral is something which I don't want to justify except saying that Pythagoras led the way there. This looking at the squares, adding the squares, x square plus y square is the length of a vector, x square plus y square plus z square is the length of a vector in 3 dimensions. What do you do with functions? You add the squares of its values everywhere and take the square root. What do you do with a continuous function? You integrate the squares. Okay? So when you put the notion of a size following Pythagoras, that is called L2. It turns out that this great Pythagorean notion is also vital in points to technology, science, physics, quantum mechanics. Everywhere it is this space L2 which occurs. So on this space L2, on which translations act, these pure nodes are not in L2. They are really from outside L2 because they are going on forever and ever. So they are not finite square integrator. But every node decomposes in their term. That is the spectral decomposition for this operator. Because if you apply this operator, you will see all these are again, these pure nodes are again vectors for it. And then this operator very correctly reappears in quantum mechanics as the momentum operator. It's related to this translation, and that's again consistent with Eminothus' theorem, who said that to every symmetry there should be a conserved quantity. So this is the conserved quantity for that symmetry. Okay, so this may mystify people who have not studied physics before, but you are welcome to ask me later. Now let's look at two dimensions. Before I go to physics, I want to look at the two-dimensional case. What happens? So suppose I have a plane and I want figures on my plane. Instead of sound one-dimensional, I have two-dimensional plane. Then I think of waves traveling on my plane. Those waves have different wave vectors and they are traveling in different directions. What will happen to these waves under my Euclidean symmetry group? The wavelength will not change. The phase will change and the direction in which the wave vector pointing will change if I rotate the plane. But otherwise the wavelength is what is invariant. So this is the invariant operator in the dual space or momentum space as it is called. I would have loved to explain to you what is momentum space or dual space, you can ask later. But many of you already know it. So take the multiplication by this in the dual space, that is an invariant operator under Euclidean group of functions. But multiplication by this is under Fourier transform exactly the Laplacian in the original space. So it is this operator, the Laplace operator, which gets born out of symmetry considerations. This is the remarkable thing, that all these important differential operators are born out of symmetry, born out of Euclid's idea of deciding whether duster is longer or chalk is longer by moving one of them. Out of this come all these differential operators if you just follow the mathematical logic. Now something wrong. What should I do?
Escape on the keyboard. Press escape on the keyboard.
So this operator, you do any Euclidean motion, this operator remains as it is. So its spectrum decompose everything in terms of this operator, and those are going to be pieces, elementary pieces, which are taken into themselves. Now, Nitsure said that the purest nodes, the simplest figures in time are the pure nodes, or the simplest figures in time. There is something atomic about them, right? We said how other things are built in terms of them. We also said that they are irreducible one-dimensional representations. They cannot be further cut off. Pure node cannot be further cut off. Everything else is built up of that. Suppose we are doing chemistry, what will you call such objects? You will call them atoms. If we are doing particle physics, what will you call them? Elementary particles. So the elementary particles of sound are the pure nodes. The elementary particles of functions, mountains, whatever it is on the plane are these plane waves. And the Mackey machine comes in here showing that indeed they don't further decompose. You get irreducible representations. I have written the formula for this representation. I don't want to spend time explaining this formula, otherwise it will go on a bit too long. You can ask questions again. So this is all very solidly mathematical, but the mathematics has come out of ideas which I explained to you. Where it came from? It came from studying functions on the Euclidean plane, moving them around under Euclidean motions such as translation and rotation, and trying to decompose these various figures into some kind of atomic elementary figures out of which everything is made. And to see that our putative atomic elementary figures cannot be further decomposed. This program leads to considering this space L2 of the Euclidean plane as a representation of the Euclidean group E2 and decomposing this unitary representation into a direct integral of irreducible representations, identifying those irreducible representations, calling them atoms, and showing how everything is built up of that. And then understanding this whole thing instead of motions, understanding it locally in terms of differential operators. The only differential operator which is born is the one invariant under this, all other operators will be made of this. When you understand something in terms of differential operators, physicists call it wave equation. They will say, give us the wave equation. Don't tell us about this global, this, that. What's the wave equation? Because one of the ideas of physics, very powerful idea which went very far, is physics happens locally. You tell us what equation is satisfied there and we will know how it is there, and that's how we will know it everywhere. So that local point of view will say, okay, solve the Laplacian. The spectrum of the Laplacian and the eigenspace of Laplacian is what is going to give you this decomposition. This way or that. Say, equal. So this stuff which happened in mathematics, Frobenius did this kind of stuff around 1900, but Dirac was at it, he didn't succeed. Dirac asked the same questions for physics starting from 1928. Wigner solved them in physics in 1947, and the general machinery for doing all this, applicable to everything, mathematics, physics, everything, was around 1950. So you see how the long mathematical evolution, Frobenius, Laplace, Fourier analysis, harmonic analysis, the functional analysis which went into talking of L2, Lie groups and the representation theory, all this long history of mathematics led finally to the solution, rapidly repeated in the last 50 years of the same evolution in mathematics, or in physics. And this is not such a great mystery. You shouldn't think that by some mysterious force those guys had the same idea. If you look at who are the people they were in close contact. Wigner spent his time in Princeton, where he was in daily contact with von Neumann, who was instrumental for many of the mathematical developments. Both von Neumann and Wigner were Hilbert's research assistants in Göttingen. And in Princeton, the presence of Hermann Weyl was there all the time, guiding these people about Lie groups and all such associated ideas. So some kind of co-evolution took place towards the end of this period. So let me move to now let's begin with physics. So in physics, space is replaced by space-time and points are replaced by events. Something happens and all those happenings form an R4. What is the structure on R4? So this was revealed only very slowly, but Galileo had an idea of an inertial operator, inertial observer and inertial frame. So just as we have procedure for laying out a Cartesian coordinate system on a plane, Galileo had a well understood procedure for setting up an inertial coordinate system, as we like to call it. Because Galileo was a bit ahead of coordinates being discovered, right? So he called it inertial observer, but what it really means is how the inertial observer will do his observations and give them numerical values, which means how he will set up a coordinate system. So this is like history with hindsight. So Galileo gave a procedure for setting up inertial coordinate frames, and he also said how they will be related to each other. So that is the Galilean group, and his main point, his first law was any two such frames will be related to each other by velocity which is a constant velocity, and whatever amount of rotation has taken place is constant. Now afterwards it's only a translational velocity. This statement, if you translate in modern terms, he was saying that the space-time is affine. There are some straight lines here. This is the import of Galileo's first law. Otherwise one may say, why do you want first law? Second law is there. Oh sorry, I have stopped naming the number of the slides. Anyway, so why do you need the first law and the second law? After all, f equal to ma. So if a is 0, f 0, whatever, but f equal to ma is always satisfied by defining f to be ma. So that doesn't do the job of the first law. First law says that space-time has an affine structure. Okay, so Galileo gave out the transformations. If you look at these transformations and if you say, what is it about space-time that these should be the transformations? What are the invariants? Just as the Euclidean plane had that Pythagorean metric, and all those transformations were transformations which preserved that metric. What is it about the Galilean space-time that is being preserved by this constant relative motions and fixed rotation? So those things are a constant one form. There's an affine structure, there's a constant one form dt. Constant makes sense because it's an affine space. And a constant Euclidean metric on kernel of dt, meaning if two events are simultaneous, only then you can tell the distance between them. If they are not simultaneous, you cannot define distance between them. So in mathematical terms, this means the Galilean group is the group of affine transformations which preserve this, and it's a semi-direct product again. So one can ask, on space-time now I have functions, I have mountains on space-time, so to say, what are the elementary figures, what are the atoms there, how to decompose it? One can ask all those same questions again for this group. Now in those days they didn't ask because these questions were not known. By the time these questions came to be asked, people already know relativity, so they asked those questions for relativity rather than Galileo. But you can now ask these questions and you can Google them, and Wikipedia will tell you the answers to these questions in particular. Okay, so I won't say more about this, but it's very instructive to take all your knowledge of modern group theory and function analysis and whatnot and go to the days of Galileo and apply to Galilean physics and see what it gives. Then you can appreciate what relativity gives us new. So let's come to relativity. So relativity, again, strange historical sequence. Just as for Euclid, the group of motions was there first, and the Pythagorean metric needed real numbers for its definition. It came much later. It's not there as Euclid's formalization. It's something which moderns deduced. Similarly, in the compacted history, the Lorentz group came first. The Minkowski metric came centuries later, meaning in the fast forward of physics, decades later. So Minkowski metric came in 1908. Probably Lorentz transformations are 10 years older than that. So group first and the metric later, but you can define the metric in terms, the group in terms of the metric as it is the group of all transformations which preserve this metric. And those transformations are automatically linear, not necessarily homogeneous, but linear. Therefore, there are straight lines in Minkowski space-time, so the affine structure is already there and you don't need the first law anymore. Once you have the metric, first law is not needed. Okay. Conversely, if you take that group, then every invariant can be built out of this invariant. This is the master invariant and all the invariants are made out of that. So let's look at the Lorentz group, proper orthochronous, because of metric orientation, all of you know this. And then the Poincare group is again such a semi-direct product like this. So instead of translation and a rotation, you are going to have translation in space-time and the Lorentz transformation. This is what makes the so-called Poincare. Now, it has its, what this group is very important. Let me say it very rapidly what this group is. What is this Lorentz group, for example? L. So, if you look at the sky, you are looking at stars and light coming from them. So, you are looking at the past null cone, basically, and the whole line in the null cone is becoming just one point on your edge. Two stars, one behind the other, and the same. Okay. Now, suppose you sit in a rocket and start moving or whichever way they like it, start walking over here. The sky picture will change. Yeah? How will it change? It will so change that the angles are preserved. There are all those strange animals in the sky, lion and this and that, and there are various animals and there are various nice figures, and between them there are those angles, and depending on that something happens to you, those things. So those angles will be preserved. Pictures will change, but those angles will be preserved. So these are conformal transformations of the sky. The group of these conformal transformations, and they are preserving the right versus left orientation, of course, being connected, is this group SL2C or PSL2C, which acts on this projective line. This here is the projective line by a fractional linear transformation. So this is the group PSL2C. Its universal covering, what you will get if you try to do the theory of spinors, is SL2C 2 by 2 matrices with determinant 1. This is where this group comes from. So the Poincare group, if one, instead of taking Poincare group, one puts in spin structure, then instead of PSL2 one has to put SL2, and you again have the same kind of semi-direct product as the group of all transformations of the special relativistic spacetime. I am taking some care to state what is that group, because I told you that it's not enough that transformations form a group. It is what that group is which determines what are the properties of the geometry. You look at this whole group, and its group theoretic properties tell you what are the various representations, what are the irreducible pieces, meaning what are the atoms, and how they may be related to other structures, to group homomorphisms, etc. One can also do this kind of thing in 2 plus 1 dimension. Instead of 3 plus 1 dimension, meaning you suppress the Z, then you will have 2 plus 1 dimension, you will get another group, that which is called SL2R. Okay, so now let us come to the main question of physics. Now I request the, what one should say, forbearance of the physicist audience for somebody saying such things. So you can of course correct me later, but this is very impressionistic account as I see things. Okay? Physics is a very wonderful and vast subject in which there are all kinds of very, very important questions. So picking out some and calling it the main question of physics, of course, is to be taken in the spirit intended. Okay. So this is the main question of physics. This question is, क्या होने वाला है? So of course, the beginning they type, है ये ऐसा है तो अब क्या होगा? Okay? This is the main question of physics. You have something called the state of the world. हाल. हाल कैसा है? So there is a state of the world, and then you say बाद में. So of course there is orientation, dt, oriented space-time, and बाद में क्या हाल होगा? So there is some evolution. This is one of the questions of physics. The other question of physics is, अरे तुमको ये हाल ऐसा दिखता है, दूसरे को दूसरा अलग दिखेगा, right? So how does the same state appears with respect to another inertial coordinate frame? We are all very impartial people. To you it appears like that, to him it appears something else, and so on. What is the truth? Actually, I should tell you, Einstein wanted to name his theory as invariant theory. But then people told him invariant theory is one of the main areas of mathematics in his day. Even today it's very important. That name is already taken, so you have to invent something else. So then he said, okay, relativity theory. But then, unfortunately, this gives a popular wrong impression. Right? Invariant theory would have given the right impression. You are looking for those things which are invariant. That is what is physical laws or truth or whatever. You don't want it to be relative. See, yes, things are relative, but you want to find the hidden invariance from all this group action. Okay. So, what is the state with respect to other inertial frames? But these two questions are combined into a single question, because among these transformations, I can take this translation vector to be of the kind only t coordinate is non-zero and other coordinates are zero. T coordinate is positive and other coordinates are zero, which means I am translating everything into the future. I am translating my frame into the future. So my t equal to 0 is now, but for that translated frame, t equal to 0 is my 3000 AD or whatever it might be, or many seconds later or whatever. So that's just a Poincare group translation. Just as other person's point of view is also a Poincare group translation. So the only question you are asking is, how does the Poincare group act on the states? This is the question. So now you have to ask two things. What are the states? States are some kind of figures in space-time. And how does the Poincare group act on them? So we are back to the basic question of Euclidean geometry. See, the basic question of Euclidean geometry is what is there on the plane, and under congruence, how do you classify it? How does it behave? How does it break up? What are the atoms? How to assemble everything out of those atoms, etc. Same questions again. So people who were doing all this, of course, noticed this, that we are back to the same question. And the person who phrased it like this, that what we want to know in physics is how the Poincare group acts, was Wigner. And Wigner solved it for Poincare group and found the atoms. So now, of course, you shouldn't call them atoms, you should call them elementary particles, because the name atom was taken by the chemists who were not willing to yield it back to the physicists when physicists managed to break it. So then chemists should have agreed that okay, these are not atoms, you guys take atoms. So electron is one kind of atom, proton is another kind of atom. Then after some time you realize that no, proton is not an atom, something else is an atom. But anyway, chemists latched onto this word atom and refused to let go. Are there any chemists in the audience? Okay. So now let's use the word elementary particle. So Wigner asked the question, find out this unitary represent, find out all unitary representations of the group of space-time with spin structure added, therefore this group P hat. And what are the reducible representations? Classify them. Now the classification came out like this. The classification was in terms of two numbers. One was the rest mass of this elementary particle, and the other number was something called spin. This spin was a property of this representation. Inside this group, Lorentz transformations, there is a special subgroup of rotations also. And then its representations have to do with how things appear when you turn things. Emmy Noether has told us that every time there is some symmetry of turning, etc., there is a conserved physical quantity, and that quantity is called angular momentum. So this other number which comes out of representations which are induced, technical word is induced in the Mackie machine sense, using the orthogonal group or its covering group, which is called the special unitary group SU2. Those representations, the corresponding particles acquire something called spin, which is related to angular momentum. One should also ask how it happens locally. To answer to that, this is addressed exactly to people who know such words. This group leads to a Casimir element, and the Casimir element leads to a certain differential operator. This differential operator is the operator which gives angular momentum in quantum mechanics. So that's how angular momentum gets linked to the spin. And so Wigner made the discovery that mass and spin will be the two properties of these elementary particles. And then indeed people, and those spins can be, well, if the rotation group itself gives the representation, the spin is called integral, but sometimes it comes from this two-sheeted curve. When you go all the way around, things get twisted. Those are called half integral. And by then, people had found particles which behave like this as well as like that. So this simple pattern, which Wigner discovered by doing pure mathematics, happened to match what physicists had found in their lab about electrons and other particles, which showed that kind of behavior actually. And the differential equations which were satisfied, the operators like Dirac operator also came out of such, like we found Laplacian Dirac operator comes out of similar considerations. Those operators really were giving the equations which those particles had to satisfy. But all of Wigner's analysis is independent of the field equations. It is completely symmetry dependent. So he said, given space-time group is this, the conserved quantity is such and such, and the elementary particles should be distinguished by this and this. But then, in actual world, the situation was much more complicated. So this slide I should show. Any unitary representation decomposes into sum of irreducible representations. Irreducibility must correspond to physical indecomposability. Therefore, these must be elementary particles. So Wigner applied the Frobenius theory to this to get irreducible unitary representations. And Bargmann completed this part of it 10 years later. Bargmann found that the representations of SL2R fall into 3 different categories. Those are called principal series, discrete series, and complementary or supplementary. What are they called? So, Harish Chandra went ahead and constructed discrete series for all kinds of semi-simple non-compact groups. So, this was starting point for the work of Harish Chandra. Bargmann, who did this great mathematical work, was a physicist, Einstein's assistant in that same Princeton Institute. So, he was again in touch with all these people and was also co-author. Okay, so now let's come to this last part. And in the last 5 minutes of my talk, I started 5 minutes late, please remember. So, one finds that the actual physical particles have many other properties. They have charge. They have all kinds of funny behavior. They interact with each other. It's not just the space-time group and its symmetries give mass and spin and that's it. There are other things. So can you incorporate those? And the idea invented for that, which was invented by Hermann Weyl, called gauge theory, and which was successfully implemented in physics. And Hermann Weyl didn't say what will be the group and what will fit where. All that was done by Yang, Mills, and various others. And I don't know the names, but it went on till 1970 and resulted into something called standard model, where the group is taken as this. And the group of space-time is supplemented by this as a direct product, and now one looks for symmetries under this. And the local equations written are called Yang-Mills equations. Physically, the extra structures introduced are principal bundles under this extra group on space-time and their associated vector bundles under different representations. The Hilbert spaces are made out of these bundles using distributions and associated symmetric spaces and whatnot. Very complicated constructions, but fully geometric. Means that what is the action of this on the state? क्या होगा और दूसरों को कैसा दिखता है? These are still the main questions. Now we come to the 2 challenges with which I am going to end. Now these elementary particles are not on their own. They are doing something to each other. They are changing each other, and their numbers are even changing. They come into being, they disappear, they collide, they do all kinds of funny things. You want a theory which incorporates all this. Unfortunately, and this is a challenge for the mathematician, there is no such theory. There are all kinds of rules of thumb to get answers in many interesting situations. With fantastic accuracy, they have found answers to many experimental questions. But there is no mathematically defined theory that this should be this integral should mean this physical quantity means this in mathematics, and this theorem is one. This kind of complete translation into mathematics does not exist. In other words, a mathematician will say quantum field theory doesn't exist. Okay? It has to be made. Forget string theory. String theory doesn't exist is now known to almost anyone. Even quantum field theory doesn't exist. So the hope was string theory will exist and answer this question. This was the hope. That maybe those questions are easier to answer via string theory and this question will get answered. But even that hope has receded. So this is question number 1, how to make a quantum field theory. And second question, considering everything was based on symmetries and general relativity tells us that space-time is wrinkled, gravity creates bulges, valleys, and then it's no more symmetric. Space-time is not homogeneous at all. There could be a black hole somewhere and really there is nothing. You cannot translate and rotate a space-time. Now remember, the chief question of physics was, how does the state change under Poincare group? Now take away the Poincare group. There is no such thing. Now what's the question? What are you talking about? So the question of physics disappears. The main question of physics needs to be framed. You can frame various local questions where you have some local approximation, do some tiny experiment which is really confined to the lab, where you may approximately behave like it is Minkowski space, and for a small duration now tell me what will happen. Like the scale of time in a particle collider, it's not very long time, it's a tiny region of low curvature. You can still try to approximate to your various things, but really the question of physics has disappeared. How does differential geometry tackle it? Differential geometry is not about evolution. It is studying different kinds of spaces with their Riemannian metrics, different structures on them, operators, their eigenvalues, all kinds of things. But that question is not a differential geometry question. So it is mathematics, but the physics question goes out. So the whole question of how to do quantum mechanics and this kind of physics on a curved space-time is again unanswered. When you hear such things that, oh, there is something quantum gravity, is the theory of quantum gravity, all that they mean is some kind of fake gravity. It's treated as a tiny fluctuation on the Minkowski space-time as a separate field instead of something affecting the symmetry group at all, symmetry group remains quantities. So it's a very different toy theory which they are trying to set up. That also seems to work in some funny dimensions and whatnot. So these questions still remain, and considering there are a lot of young people in the audience, these are very important questions, and the progress made so far is very suggestive that something is right about what they right now know, right? Not for nothing they have found Higgs at the expected things, not for nothing there are all kinds of fantastic answers which are so accurate. So they are doing something right. Yeah? Now somehow maybe the correct mathematics is waiting to be discovered. Whatever it is, whosoever does it, it will need that kind of Princeton atmosphere where people know these different things, talk with each other, in close collaboration, ideas are exchanged, and the theory gets built. Tata Institute should have ideally been a place of this kind of interaction. Maybe it may still become if the future generations succeed at it. Thank you very much.
Thank you very much for such a wonderful talk. And I can really see on the face of all the audience, and also, as you said, this coming together, all the different faces, different people with different skills. So that's all I think already there in the audience, and also different generations of people.